Very good. So I propose to restart. So it's a second lecture in which we are going to work to learn about how to use class, starting from the most basic things and going into more advanced usage later in the afternoon. So we already went through the installation. Now I assume that, so I think two people maybe need a little bit more help to finish installation, but it means that the bulk of people can already train. And when I will say, you just need to do this, you can feel free to do it online and feel free to interrupt if something is not clear. So where do you find documentation for the code? So when you develop a public code, the documentation is always very painful because you spend a lot of work of time on it, and still you realize that people have a hard time finding where the information is. You get lots of questions by people who did not try to read the documentation, but you cannot blame them because you were maybe not good enough to say where the documentation was. So this is all a complicated business. And yeah, so here are some important links. So first, if you go to the old class web page, which is always maintained, classcode.net, you will find lots of comments, for instance, on the different versions of the code. And you will find a summary of all the interesting links. In particular, you will find a link to the automatic documentation. The automatic documentation is a thing which is generated by Doxygen. When you download class, you get it in PDF. So you have it locally in PDF on your computer in a directory class/doc and /PDF maybe. But if you use it online, it's nice because it's full of hyperlinks. So the online HTML documentation is here, and you find the link from classcode.net or from the Git repository. And then if you click on this, and I invite you to do it now, if you found the link, you see several sections. The first three sections are not generated by parsing the comments in the code. They are generated independently by us. The first one is called Class Cosmic Linear Anisotropy Solving System. It gives some general overview. The second section is where to find information and documentation on class. And there you see lots of links to physics paper that explain the underlying physics, or sometimes to notes that we wrote in order to document a given aspect. So this is more about the physics. About the code, the third section here is important. It explains the class overview. It explains the architecture, the format for input and output. More or less, it replaces the lectures it condenses the lectures that I'm doing today. When class was released in 2011, there were 4 papers, and the first one was called Class 1. And this Class 1 contained more or less this information, but this one is more up to date. Okay, if you want to find information at a more advanced level, so you have lots of links in my web page and clicking on courses. So I've done lectures similar to this one in many places, and some were less detailed than in New York, some more. So you could be curious to have a more detailed version than what I'm doing here. And for this, for instance, I recommend the version from Tokyo IPMU, because there we had 1 full week, so we gave more details on the code. So you can see all the PDFs, the slides of the lecture there. Okay, and for a more advanced usage, so in this automatic online documentation, after the 3 introductory sections, you see the part which is generated by Doxygen, and then you can localize your function and find the tree of dependencies of this function. And from there, you can click on one of the functions calling it, or the function it calls, and you can navigate quickly through the logic and the tree of the code. Okay, this was documentation. I know it's imperfect. I know it can be improved. Any suggestion for this is more than welcome. So next, I suggest that you have a look in your class directory. So if you download it from Git, it's probably called class public 272. This is the current version. And inside there, you should see at least these directories. The first directory, source, is the most important one. It contains the 10 modules of class. This is where all the physics is. Tools also contain some C code, but this is all the numerical methods, not referring specifically to the physics. So in other codes, we would have decided to use some external libraries, and we wouldn't have these tools. But because we are self-contained, all our methods for integration, interpolation, integration, they are all in these tools. Main is very short. It contains a main function that just calls the 10 modules. So this main function is used when you run class online. When you call it from a wrapper, like the Python wrapper, it's not even used. Test contains some alternative to this main. This is useful during development because the 10 modules are called sequentially. When you call class, the main of class, the 10 modules are called. But it's completely possible to run class until a given module. So suppose that you are doing some development in the third module. When you want to compile and test, you don't want to run the 10 modules, but only the first 3. And for this, you will find in test some alternative to the main that only calls the code from module 1 to module n. Output is where the code will write the output if you run from the terminal, not if you run from a wrapper. Include are the usual feature in C. It contains all the header file. So this is where the structures and the functions are declared. Doc should contain this PDF version of the deoxygen manual. Python contains, of course, a Python wrapper. CPP, a C++ wrapper that was developed by a group in Paris at LAL. It's a group of Plasinski et al. I'm not using C++ much, so I don't know so much about this wrapper, but it's supposed to do more or less the same as a Python wrapper. In notebooks, you find some example of notebooks that we will comment in this lecture. And for instance, if you want to reproduce one of the figures that I showed at the very beginning, you already have the script. So instead of writing your notebook from scratch, maybe you want to start from one of these and adapt it to your needs. And if you don't like notebooks or you cannot figure out how to install Jupyter, in scripts, you find the same script, not in notebook style, but in plain Python style. And real space interface contains the funny outreach code that Christian showed you before. So if you want to use the real space interface and play like Christian, go there, read the README, which is inside, and it will show you how to launch the interface with 2 commands by running something in the terminal and then pasting an address in your browser, Safari or Chrome or whatever. Okay, there are a few more directories, less important. They contain some ancillary data, like data from BBN, and some are very important. They contain nice external codes, like HiRec, the code of Yassin, which is an alternative code to compute recombination at much better precision than the inbuilt recfast. External PK, we will come to it later. But all these other directories are for external codes or pieces of information that are interfaced with class. Okay. Where am I? Yes. I was in page 7 before. Yeah, this is a bit slow. No, I didn't do page 7 already. Okay, so page 7. You want to, if we are going to start by running from the terminal, because you need, before running, you need to learn how to walk. So we will start from the terminal. But I hope that I will convince you that very quickly you should abandon this and do everything from Python notebooks. So if you want to run from a terminal, your input parameters should be in an input file ending with .ini. And we provide the public class with several .ini, and the first one is very special. It's huge. I don't know how many lines it has. Maybe you can count. I'm sure it's several hundreds, maybe thousand. I don't know. You can tell me. Why is it so big? It's so big because it contains all the functionalities of class. So when we add a new parameter, a rule is that we must add it and describe it in explanatory.ini. This is why it's so huge, but you will hate this file if you use it too much, because it has maybe 200 lines for isocurvature mode, and maybe you will never care about isocurvature mode in your life. So you should consider it as more as a documentation, something you can look at to check what are the possibilities. But you want in your everyday life to work a slim file, a small file matching your needs. So for instance, these two files that we distribute will only run the baseline model of the Planck collaboration, which is a lambda CDM model with one massive neutrino with a fixed mass of 0.06 electron volts, and with parameters taking from the best fit of Planck 2015 and 18. So instead of 1,000 lines here, we are probably down to 30 lines or so. It starts to be nicer. So this explanatory.ini, being like a full documentation of the code, should not be modified. You should avoid the temptation of writing your modification in explanatory.ini, because if you do, it's no longer a reference code. What can you do? You can copy it to toto.ini and modify toto.ini. It will still be very long, but it will have all possibilities. Or what I recommend is that you start from one of these slim files. For instance, you start from a Planck best fit file, and if you want to add dark energy, you add 5 lines with your dark energy parameter. You really don't need to work with a big file with all the parameters, because all the parameters have default value, which are always straightforward. The default is always Planck lambda CDM. So you really don't need to say that there are no isocurvature mode or no decaying dark matter. The code will always assume it by default. You can trust this. Okay, and the third way to work, this is how I do, and this is probably how people do after just a few days of experience. You start from a blank file, and you write just 10 lines in which you are interested. And this is really the quickest way to proceed. So let's go through examples. I suggest now that you try to run this file, which is the best fit of Planck 2018. Okay, so .class base underscore 2018 tab completion on your terminal, and you get some output. You notice that the code runs in, depends how many cores you have on your PC, but the order of magnitude is a second. And you get many lines of output, and these are interesting information that are given to you as a user because they are not things that you passed in input. So for instance, the first line says omega lambda is 0.68. As we will see, you don't pass omega lambda in input. It is adapted to match the budget equation. But then you want to know what has been used, so you use this output to be sure. This is written first because it's in a pre-phase of interpreting parameter. Then the class modules really start, and it gives you a lot of lines of output. I have only put a few here, but there are like probably 30 of them. You know the age in gigayears that you could not guess in advance. A few characteristic redshifts like radiation matter equality, recombination, reionization. There is a warning here about something with halofit. It's because this file was requiring nonlinear corrections to the matter power spectrum with halofit. Now, don't worry, you will understand what this warning means. It's completely normal. It means that everything worked well. You will understand what it means when I will, during the theory lecture, which is the next one. You get your sigma 8 and the value of k until it has been computed. So if you work on large-scale structure, you know what sigma 8 is, and you understand that it's nice to be sure that it was not computed up to a too small k, because if this was the case, the integral will not be converged. This is Paco's special. as we will, yeah, I think we will come back to this. Now, when you have massive neutrinos and you want to compute observables related to galaxy lensing or halo mass functions, then you realize that galaxy density or halos are not tracer of the total matter power spectrum, but of the matter power spectrum of only cold dark matter and baryons. So class knows this, and when you switch on a non-zero neutrino mass, it will duplicate all your output observables. You will have everything computed from total matter and everything computed from cold dark matter plus baryons. And so you have two values of sigma 8. And depending if you are doing weak lensing or galaxy clustering, you will be more interested in one or the other. Okay, there are lots of other things, and the CLs and the matter power spectrum are being written in the output directory, and the code tells you where. It says in output, and then you get a suffix here, and the suffix matches the input file. So I will tell you what the logic is for choosing the name here. Essentially, the code first tries to have all the output file starting like your input file, plus the first available number. So the first time you run, it will be this and 0, 1. And then if you rerun, it will detect that there is a 0, 1, and it will write in a 0, 2, then 0, 3, etc. But sometimes you want to choose the name of the output, and you don't want to generate a new output each time you press class. So you will see that there is a field in the input file in which you impose a fixed name for the output. Okay. Is it working on your laptops? Yeah. Oh, I know that many of you also did it, used class before, and for them this is very childish. I apologize. Okay, next. Yeah, why do we have all this chatty behavior? Maybe we don't want this chatty behavior because maybe we want to run class in a big loop and we don't want our output to be polluted with hundreds of lines. So there are verbose parameters in class, and there is one per module. You can choose them independently. And in this file, the verbose parameter of all modules were fixed to 1, which means give only the most useful information. You could have fixed it to 0, you would get no output, or 2, 3, 4 to get more and more information useful for debugging. So if you look at this file, these verbose parameters are the last 10 lines. If you do a tail of this, tail by default gives you the 10 last lines. So if you do tail of this file, you will see 10 values set to 1. Okay, so now I suggest that you try to write your mini input file. And this is a very short one. And really, you see that you don't have to be scared about the length of explanatory.ini. You should never run with a full explanatory.ini. So I assume that you, with your editor, you create a mymodel.ini. And to get a minimal number of things, you can write an output field. So you can set the output to TCL, PCL, LCL, MPK. This means the CL of temperature of the CMB, the CL of polarization of the CMB, the CL of the lensing of the CMB, and the matter power spectrum. A remark, in other codes, you would find here a list of modes like TT, TE, EE, BB, etc. I told you class is always trying to use its own logic as much as possible. So if you have entered TCL and PCL, the code knows that if you have no primordial gravitational wave, it should compute TT, TE, and EE, which is the maximum it can do. And if in another place you say, I want tensors, from the same input, the code will say, I can also compute now BB, so I will compute BB. So all these little choices, all these little decisions can be taken by the code, so they will be taken by the code in order to have a light input. This lensing equal yes says that the code will try to compute the lensed CLs. Don't confuse lensing and LCL. LCL means compute the harmonic spectrum CL of CMB lensing. So the spectrum of the projected lensing potential. While lensing computes the lensing of the CLs, which is a second order perturbation effect, starting from the unlensed CL and the lensing CL. Nonlinear is where you say that you want your halo fit corrections for the power spectrum. Root is where you can choose the output file, and then you avoid to produce a 01, 02, 03. If you fix it, it will always overwrite in the same file. I recommend this write warning. You should always try to put it set to yes. This write warning has a property that if you mess up a line of input with, for instance, you remove the S here, the code will tell you this line makes no sense for me, I ignore it. If you don't have write warning set to yes, it will not do this, and then maybe you will never know that you had done a syntax error. So you should set it to yes. Of course, if you do a typo when you write write warnings equal yes, you will never know that it does not work. This is the only caveat in the logic. Okay, so what is the overall syntax of this? So this is parsed by class, not by some predefined library. Class has its own parser. And the first thing that class does is to, when it reads a line, is to remove everything after a hash, keep the rest, and check if there is an equal sign. If there is an equal sign, it says, it's interesting. If there is no equal sign, it says it's a comment. So when you have a line with no equal sign, you don't need the hash. This is not a problem. It doesn't have a hash, but it has no equal sign. This comment has an equal sign, so I had to mask it by putting the hash before. Okay, and then when the code finds a nice group like this, something equal to something, it knows that its name equal to value. The values are always read as strings. And then if this string is a number, the string is parsed to a number. But sometimes it's just a string, it's a code for something. For instance, each time that you want to say that something is yes or no, what the code does is to look if there is a Y or an N inside. So if instead of yes, you write yep, it works also. Yeah, that's it for the syntax of the input. Okay, so the order is totally irrelevant. You can really reshuffle these lines as much as you want. Each time that a parameter is not passed but is needed, it will be set to a default value. For instance, here, we have not set any cosmological parameter, so automatically we are going to run a minimal lambda CDM with massless neutrinos and 6 lambda CDM parameters fixed to a default value. I told you we don't like to update the code too often, not to confuse users, so it's still Planck 2013 if you don't pass the values explicitly. Because if you don't pass the value, probably it means you don't care. You want to see a global shape, so why not this one? Okay, at some point we will update it 2018, but if you want 2018, you use one of the files I gave you before. Yes, so suppose you write this and you run class_mymodel.ini. You don't have these output lines when you run. You don't know the age of the universe and all this. Because the verbose parameter are 0 by default, so you get no output. If you want the verbose parameter, there is a trick. You don't need to write the 10 lines manually with the risk of doing syntax errors. If you do tail explanatory append mymodel.ini, it will take the last 10 lines of this one and add this to your file. So the 10 verbose parameters set to 1 will be copied. So we do this a lot. It's why, in fact, we try to keep the number of verbose parameters to 10 such that this trick works. Okay, after doing this, if you rerun, you will have all these nice outputs. Is it important to have a .ini? Well, class will accept two formats, .ini and .pre, because they are input parameters which controls the physics and the nature of the output, and they are precision parameters. And it can be convenient to have some files with a .ini, which are like cosmologies, and some files with .pre, which are precision settings. And then if I want to try 5 cosmologies with low precision and 5 cosmologies with high precision, I still don't need to write 10 combinations. I will keep one of the two .pre. However, the code is not picky on what goes in each. You are allowed, this is just to make your life simpler in some cases, but you are allowed to write your precision parameter settings with the same syntax in the .ini and always use a .ini. So the code doesn't know any rule on what should go there and what should go there. It's just a suggestion. So there are a few .pre which are distributed with the codes. There are not too many. I think there are two interesting ones. So by default, the code will run with a precision sufficient to do an MCMC with Planck and Bose, say. Okay. Now, if you want high precision, usually you don't need higher precision because either you have real data and the precision is okay, or you do a forecast, which in principle would require high precision, but because it's a forecast, you don't care about having the high precision. So usually you don't need to increase the precision. If you do, the precision on the CLs, which is a critical thing here, is of the order of 0.2, 0.3%. If this is not enough for you and you pass CL per mil.pre, it has been preset to increase the precision to 0.1% precise CLs. If you do something more advanced and you want a reference model, you want to be sure that you coded something at a given level of precision. It's important for you, you are ready to spend 1 hour of CPU time on that. Then there is a clref.pre. The clref.pre is exactly what gives the 0.01% agreement with a version of COM in which you push all the precision parameter to extremely high number. So in these very high precision settings, both COM and class take about 1 hour. You need to be patient or to run it at parallel on 10 threads or something like this. So CL per mil is still fast and more precise. clref.pre is very slow but very precise. It's not only very slow, it requires a lot of memory. So maybe your laptop will complain. Depends on the characteristics. Okay, questions on this? Good. So what about the results? So the results have been written in the output directory with, and in the previous example, we imposed a name. So there is a prefix, and then there is a part which is named automatically by the code, like CL, CL length. So the most customary one are the CL length, the CL with nothing, which means unlengthed, and the PK for the matter power spectrum. We will see there are other ones if you call for other functionalities. So if you have this, so first, if you use a Python notebook, it's another story. The output is not written in files, but is stored in your variables in your notebook, and you will directly use pyplot to plot it. So here I'm really taking the case of somebody running on the terminal. So you have your data in this .dat, and you want to plot it. You do whatever you want. You do MATLAB, IDL, GNU plot. But if you are in a rush, we prepared something for you which is optimized for class. It's a class plotting unit. I don't like too much this name, but a previous student of mine found it funny, so we left it. And he did it well anyway. So if you do python cpu.py --help, you see lots of options. So it's a Python script. What is the advantage of using this Python script is that it already knows a lot of the convention that are used when the output is read. So for instance, it will read the headers of these files. A class output always has header, unless you switch it off. It has always header explaining units, name of variables, ordering of columns, such that you can always open the file and be sure of what is really there. So cpu.py reads these headers, and this is why it's efficient. For instance, if you do the first command, you see lots of lines because you get all the length CLs for temperature and polarization. Okay. So you can be a bit confused. And to select some of the outputs, you can put a -y, and then it will select what you should have in the y-axis. And then you can put a list of acronyms with a very flexible syntax. So you could put here TT or TTTEEE, and then the code reads in the header that TT is the second column or BB is the fifth column. And it will select here only the one or several columns that you passed. With minus scale, you can make the plot log-lean. There are lots of options. There is even an option called George, minus scale George, because George Estasiou is a fan of having first linear and then log. So you can have this automatically. Okay, so you can look at these options, and this is when I'm in a hurry, I don't have time to write a Python script, but I want very quickly to check something. I use cpu.py. Yes, you can use it to superimpose many outputs. You suppose you have run 3 models with 3 different combinations of parameters. You want to compute to compare the CLTT of the 3. Then you just put Python cpu.py, first file, second file, third file. And then maybe you want to plot the ratio of 2 of them. Then you put 2 of them, and there is an option -r, and it will know that it has to do the ratio, which is not so trivial, because to do the ratio, sometimes you need to interpolate one function for the same values of x as the other function. For instance, when you output the matter power spectrum pk, the sampling of the matter power spectrum is decided by the code on the basis of the cosmological parameters. So if you have 2 files pk.dat for 2 models, their k values will be different. But if you do Python cpu.py first name, second name -r, it will interpolate one spectrum on the k values of the first one in order to give you a ratio. Questions on cpu.py? Did you try? Did it work? Yes? Nice, nice. Very good. Yeah. At some point, before we became fans of Python notebooks, one of us, Thomas Tram, was using MATLAB a lot. So there is something for MATLAB which is exactly doing the same as cpu.py in MATLAB syntax. And so inside MATLAB, if you do help plot class output, you will see all the options. Very good. Okay. This was old school. Now we go to more fancy usage, and we try to switch to Python. So this works because when you compile class with make, after compiling the C code, it will automatically compile the Python wrapper and install class as a module in Python that you can use from whatever directory on your computer. Once it has been installed, you don't need to be in the class directory to call the module. You can be anywhere. Okay, so this module was developed initially by Benjamin Audrin. It was extended by many others. And I should put a disclaimer that so far it does a job. It does what we want. And in particular, all the interfacing with the sampler codes and all what you need to do nice plots. But we are aware that it's not super fancy style, and we have plans to improve it. I will mention it tomorrow. So once you have compiled, some files are automatically added in the Python directory. And the wrapping is done through Cython. You know, it's a module of Python which allows to wrap C from Python. This is why you need to install Cython before installing class. So it does not wrap all the functionalities of class because it's still written manually. So it wraps what we decided to code manually in the wrapper. And it's not all functionalities. I think at some point it will become an automatic process that will have all functionalities, but it's not the case so far. So I will show you how to use the wrapper and see what are the coded functionalities anyway. Yeah, as I am telling you, my dream, I just need to find a motivated student. So far I failed, but I think next year there will be one. Because class is written with a very strict set of rules, it would not be very difficult to write a parser that would parse the header files of class and infer from this the wrapper. It's possible because we have some logic which always respect the same naming for function, the same order, etc. This is why it's doable. So we plan to to work on this. Once it's done, the wrapper, so the content, most of the content of this file will be written automatically at compilation. And then you will sure that all the new things in class automatically propagate to the wrapper without the need to add them manually. Okay, so the goal of the wrapper is to use these basic functionalities of class in a Python script or IPython or a notebook. And I will give now some examples. I will assume that you like notebooks. If you don't, you find the same information in this script directory. So I assume that you have no problem installing the Jupyter Python module. Then you can open one of the distributed notebooks with Jupyter Notebook, one of the name of the notebooks distributed with the code, and we will start with warm-up, which is done precisely for this kind of lecture. So after typing this, you should get the notebook opening somewhere on your favorite browser. And again, if it doesn't work, you can follow the course by typing the just normal script version. Okay, so let's comment on the content of this notebook. It will always start by importing something from the module. So what do we do here? The module is called classy. So what doesn't make things easy is that class coincides with the name class used in coding. So you can have a class for class, and lots of confusion can come from this. So classy is a Python module. And from this module, you import class, which is, you can think this class is a class of Python and contains a version of the code class. Okay. And once you have done it, you want to create an instance of class in which you will store a given cosmology. And you could do many of them. Suppose you want to compare lambda CDM with open CDM, you would create a lambda CDM equal class and an open CDM equal class. It means that these objects are the same kind of class as this, but this is a generic one, and this is a particular instance which inherits all the properties of this class. So now you will be able to do all your manipulation with this, but you can have as many instances as you want. So since you have an instance where you want to study one cosmology, you want to pass some input to this instance to run the code and to read the output. So first, to pass the input, you will call the .set. So .set is just one function of the class used to set input parameters. And there is no rule about the fact that you should call it once with all parameters at once or many times with one parameter each time. Because each time that you do a .set before a .compute, it just adds up on the list of parameters. So here, in a completely arbitrary way, I have decided to split up my input in two, but I could have kept it in one line or split up in 20 lines. In each set, I pass my parameters as a Python dictionary, which means name, value, and the value can be a number or can be a string. So here you see that I'm fixing the value of my 6 lambda CDM parameters. And here I'm defining what I want the code to compute. And it's the same example as before. We want the CMB CL, the matter power spectrum. The CL should be length. And here we also ask that the matter power spectrum pk is computed to a maximum value of 3. And here the unit is 1 over megaparsec, 3 megaparsec minus 1. If you want to guarantee a given Kmax in h by megaparsec, no problem. You have another input parameter called pkmax h by megaparsec. Just use the one you want. The code will interpret it. And if you put the two at the same time, it will complain that you are passing over-constrained input. Okay, assume that you are satisfied with all your input parameter. Now you want the code to make the calculations. And only after that, you can play with the output. So this is very simple. It's .compute. So if you have a complicated model here, this could take a few seconds. With what you wrote here, it will take the usual seconds. Even less probably for this lambda CDM. Okay? Now, all the results of the class calculations have been stored in different fields inside this class. And what you want is bring them to life, extract them from the content of the class. And for this, you have many different functions for many different observables. So if you want your CMB CLs, the length one, of course, by default, you call length CL, and the argument here should be Lmax, maximum multiple. And you want here your so it will return arrays containing the CLs, and I store them in CLS. It's called CLS because I know that I did not ask for tensors. We will see later how to do with tensors. So I didn't ask for tensors, so these are scalar CLs, so I call them CLs. Call them whatever. And then typically what is nice with Python is that you don't need to remember everything. For instance, if I've not used class for 3 weeks, I have completely forgotten how the data is arranged here, and I don't want to go to the documentation to find out. So I do a CLS view keys, and this will tell me how are the data organized in CLS. And I see that it's a dictionary where the keys are PP, L, BB, E, TT, TP, TE. It means that inside CLS, I have a dictionary with entries and then values. And the first entry is PP. PP is in fact phi phi. Phi phi is a CMB lensing potential. So this will contain the CLs of the CMB lensing. And after this entry, I have an array with values. The second entry, L, is the multiple L, written in the fancy LaTeX way, in order to avoid having just one letter. And then you have the BB mode, EE mode, TT. This is the cross-correlation between temperature and phi, so the CMB lensing potential, and the cross-correlation between temperature and E modes. Okay, so now that I know my keys, I'm going to extract, for instance, the list of values of L. So the list of values of L should be CL of this key. And CL of this key is an array of values of L that I store in LL. It's not completely important to have these two here, but it's just a way to be sure that we are going to store the L value starting from 2. You know that usually you want to get your CL starting from 2. Actually, there is an option in class to get them from 1. It's not a ridiculous problem, but by default, it will be from 2. The same with your CL of temperature, polarization, and CMB lensing. So I ignored cross-correlations. So now I should have the list of L's and the corresponding list of CLTT, EE, and phi phi. And then I want to plot them. So for this, I will use pyplot. I import my pyplot. I import a little bit of math because I want the pi number. And here there is a line that I commented out because this line depends a bit on your installation. The goal of this line is that it's very nice inside the Python notebook to have the figures appearing between the cells, because then you can use your Python notebook like Mathematica, some nice comments decomposed in cells. You write some comments to explain what you are doing, and below each cell you have the results of the calculation and a nice figure. And when you look at your notebook after a few months, you remember all the structure of your previous work. So to activate this, you must use either matplotlib notebook or Matplotlib inline, and you can try both until this cell does produce a plot inside the notebook. Okay, in this cell, we are just trying to plot CLTT. So I declare a pyplot figure number 1, because maybe I will do other figures after 2, 3, 4. And I want some log scale for X and some linear scale for Y. I want to be sure that my range is from 2 to the L max that I asked before. I give some nice name to the axis. And then I do the usual pyplot plot of the X array and the Y array. And the Y array is a CLTT rescaled by the usual factor L plus 1 over 2 pi that everybody uses in the CMB community, because then the CLTT are easy to relate to the real temperature fluctuation in real space with some mathematical operation. Okay, and you have done your usual CL plot. So if you have this, if you have Jupyter Notebook working now, I guess that you have been executing the different cells and you have this figure. And then you can save the figure in a PDF. Anybody has particular problem doing this figure? Anybody who was trying? Works. Okay, very good. Okay, so this is of course extremely basic. Don't worry, we will go into more advanced notebooks. Okay, let's keep going. In the same warmup.py, you see how to plot the PK. It's a little bit more complicated, because for the CLs, the code knows that you want the CLs at discrete values of L. So it gives you a column with every L from 2 to L max and every corresponding CL. For P of K, the code does not know which are the K values in which you are interested, doesn't want to take a decision. So what the Python module does is not a function giving a grid of K and a grid of PK. It's a function to get PK for a K of your choice. And this function is called .pk. So this is our class. And the function .pk is a function for which you give a value of K, you give a redshift, these are the two input parameters, and the result will be a PK. So we want to call this function for the K values of our choice, so we need to generate an array of K value. And here with this log space command, we generate an array of K values which are log separated from 10 to the minus 4 to 10 to the 3. Okay. So KK is now our array of values, and PK is the array where we will store the corresponding PKs. But in order to do a custom, the normal kind of plot, we want this K to mean something in units of H by megaparsec, and we want this PK to contain the PK in megaparsec over H to the 3. And so we must do a work of conversion, because if you will see how to look at the documentation of this function in a while, but this function really wants a K in 1 over megaparsec, and it gives you a PK in megaparsec to the 3, which are, as we said, the default units inside class. Everything in megaparsec to some power. So to do the conversion, I need to know small h, and of course I could remember what is the value of h that I passed, but if I had to use this, I can make a mistake, it's ugly. Better to infer h from the class. So there are hundreds of functions like this. This function .h will recall you what is the value of h assumed in this model. Now you have stored it in h. And then what do I do here? I call my pk function not for k, but k times h. Because if k is in h by megaparsec, the product k times h is in 1 over megaparsec. So it's a valid input for my function. I want things at redshift 0. And so this number, which is returned, is a number in megaparsec to the 3. And to convert it to megaparsec over h to the 3, I need to multiply by h to the 3. Now I have my pk in the right unit, and I append it to pk that I declared here blank, and progressively pk will contain all the pk values corresponding to each k value here. And then I can plot it. Figure 2, I set my axes, my limits, my labels, and I do a dot plot of the X array, Y array, and I get my pk, and I can store it in a PDF. And with warmup.py, I think you have 4 figures because you also have CLEE and CL55. So this is really the most basic thing. Of course, at this stage, it seems a lot more effort than using the terminal and the CPU.py. But the advantage is that with this now, you can do all the manipulation of the output that you want. Okay, okay, there is something we have not updated in our scripts. If you look at the end of warmup.py, you see struct cleanup and empty. These were 2 commands that were before existing in order to remove any information from these structures, first about the input parameter and then about the content of the calculation. And these functions were useful if you wanted to clean and reset everything before using the same class for a new model. Now, this is not generating an error because the code still accepts these, they are still there. But the Python wrapper has a new feature. If you try to compute a class while the class already contained another model before, the code will detect it automatically and do this automatically for you. So you don't need to call these these commands. You can forget them. But so far, they are still written at the end of our scripts because we have not updated. This is since version 2.7.2, so it's very recent. Okay? Yes. Very good. Yeah.
What are the default value and where I can find it if I want to see what's default value?
Yes. So the default value are all grouped with this logic of user friendliness. We group everything. So in input.c, there is a function with all the default value of the cosmological input parameters, and another function with all the default value of the precision parameters. So everything is in input.c. Okay, now another advantage of IPython and even more Python notebook is that you can access to a quick description of the function online. For instance, in this example, I have created an occurrence of the class called Cosmo. And I want now to do some cosmology with this. And I forgot what I can ask to this class. And if you use the tab key, .tab, you get a list of all what you can do. These are just the first option, because in fact, you will get here a scrolling menu, and you can scroll to get many more. There are many more things than this. And of course, then it's rather intuitive that cosmo.hubble would return the Hubble parameter. Of course, it will work only if you have set the input already. And NF would be the effective neutrino number. That can be interesting because the effective neutrino number is calculated for you by the code, given your input for the massive neutrinos and for the massless neutrinos. And this will return the value of the omega parameter that you used, etc. And this we will see. This will be a function, the angular diameter distance as a function of redshift. This will be a function, the baryon temperature as a function of redshift. We will see all these things later on. But this is just a principle that .tab gives you all what you can use at a given point. Okay? And then after you have completed the name of the function, maybe you forgot what are the arguments. But when you start completing this function, you write angular underscore d and tab, and it completes the rest, and it puts empty parentheses. And if after these empty parentheses you press tab shift, you get a short documentation of this function. And I know that all of them have not been nicely implemented. Okay, this is one thing we need to improve. But for instance, if you try this together with me, angular diameter distance tab shift, you see that this is the angular distance, that the input is a redshift, and the output is the angular diameter distance. And then you know the format of the input and the output. And you can write explicitly your input, for instance, Cosmo angular distance of 10. Okay, so we have 3.5 minutes left. Did you have a question on this script and how to use this warm-up script? Yes.
Just so is the only time it actually calls the main class when you type .compute? Or like
Yes, it's only when you do the dot compute that it actually runs the C code.
so that PK is like an interpolation or something?
Absolutely. So all these other functions are interpolation. So exactly, it's a very good question. So the dot set are equivalent to passing the input file. The compute is the only time where the C code is executed, and the C code writes all its results internally in some structures. And all the other functions only have the role to pick up the information from the structure and give them to you either directly or, as you correctly said, through an interpolation, as was the case for PK. Yes. Other questions? Okay, shall I start with the description of the species? 2.5 minutes should be good for this. Yes. Okay, so this is a list of the matter species that are implemented in the default class. There are lots of private versions with more, and I will tell you what will join the public one soon. There are two that you cannot spare. A Boltzmann code makes no sense without baryons and photons, because the primary goal of a Boltzmann code is to compute the effect of Thomson scattering on the perturbations. So you are not allowed to set up the photon or the baryon density to 0. They are the only species like that. You can do it for all the others. What you can do is set to a very small number to see the limit. The limit is anyway crazy. When omega b or omega gamma approach 0, the CMB and or the PK always look completely crazy. So it's not really a feature that is missing. And for each of them, I already told you, you have the choice independently between different formats. The next one is ultra-relativistic species, which could be massless neutrinos or many other things. Axions, moduli file, whatever. So they are all grouped as UR for ultra-relativistic species, and you can pass their density as a big omega, small omega, or contribution to NF, the effective neutrino number. Of course, you have cold dark matter, and we will see that there are options for cold dark matter. It can be simple, or it can be annihilating or decaying. And then there is a very rich sector called non-cold dark matter. Non-cold dark matter means any species that you want to follow in phase space with a phase space distribution and a Boltzmann or a Vlasov equation. So essentially, it's everything which is not fluids. Well, there are three categories here. There are fluids, quantities with a phase space distribution, and scalar fields. And this is the second category. So quantities with a phase space distribution are photons, massless neutrinos, and these non-cold dark matter. And for this non-cold dark matter, you have a lot of options that I don't put here, because by default, it would be assumed to have a normal Fermi-Dirac distribution like massive neutrinos. So by default, the code will assume you want massive neutrinos and you want their omega or their mass. But if you want to go beyond this, you have input command allowing you to change lots of other things, which are useful, for instance, for sterile neutrino or warm dark matter. You can change the shape of the phase space distribution. You can change its normalization, like for those who know sterile neutrinos, like in the Doddelson withdrawal mechanism. And finally, you are allowed to have many of these non-cold species, because you could want at the same time 3 normal active neutrinos plus 1 sterile neutrino plus 1 warm dark matter component. Then you would set this number to 5, and for each of them, you would set independently your properties. Our time has gone, so I will restart on the class usage after the lunch. Now we have a break, and after the break, I will go to the other lectures called class theory. Thank you.